Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In 1704, Isaac Newton's method of fluxions appeared in print, offering a profound approach to problems concerning rates of change and accumulating quantities that continue to echo through modern science. This work, born from Newton's intense intellectual engagement with geometrical problems, represented a significant advance in what we now call calculus, offering innovative solutions to challenges that had perplexed mathematicians for decades. At its heart, Newton's method grappled with the ancient problem of finding tangents to curves and calculating area, challenges of immense importance for the burgeoning fields of physics and engineering. Prior to Newton's work, mathematicians relied on methods such as Cavalieris' method of indivisibles, a technique fraught with logical difficulties and lacking the general applicability required for widespread adoption. Newton sought a more robust and versatile approach, one that could elegantly address a wide array of geometrical problems through the power of algebra. His solution lay in the concept of fluxions and fluents, a dynamic view of mathematical quantities where variables are envisioned as changing continuously with time. Newton introduced his dot notation, with a variable with a dot above it representing its rate of change. The essence of Newton's method involves envisioning mathematical quantities, such as the coordinates of a point moving along a curve, as fluents that change continuously with time. The instantaneous rate of change of these fluents he termed fluxions. For instance, if we consider a point moving along a curve, its x and y coordinates are fluents, and their corresponding fluxions, denoted by x with a dot above and y with a dot above, represent the instantaneous velocities of the point in the x and y directions, respectively. This approach offered a powerful way to analyze curves and surfaces by considering their dynamic properties. Newton's motivation stemmed from a desire to solve fundamental geometrical problems. He sought methods to find tangents to various algebraic curves, determine maxima and minima of functions, and compute areas enclosed by curves. These problems were not mere abstract exercises, they had direct applications in understanding motion, gravity, and other physical phenomena. The method allowed mathematicians to apply algebraic techniques to geometric problems. The initial circulation of Newton's method of fluxions was extremely limited. The work existed primarily as a manuscript for many years, shared among a select circle of mathematicians. This limited dissemination contrasts sharply with the broader scientific climate of the late 17th and early 18th centuries. The same era saw Gottfried Wilhelm Leibniz independently develop his own version of calculus, which, aided by superior notation and a more rapid publication, gained wider acceptance across continental Europe. The priority dispute between Newton and Leibniz over the invention of calculus became a bitter and protracted controversy, casting a long shadow over the development of mathematics in Europe. Newton was deeply influenced by the work of his predecessors, particularly Isaac Barrow's Lectiones Geometricae and John Worth's Arithmetico Infinitorum. Barrow's geometrical lectures explored methods for finding tangents to curves, a problem that deeply engaged Newton's intellectual curiosity. Wallis' work on infinite series and interpolation techniques provided Newton with powerful tools for manipulating and approximating mathematical quantities. For instance, Wallis explored methods for finding the area under the curve y equals x to the power of m for various values of m, including fractional and negative exponents. This notion proved foundational to Newton's method. These works exposed Newton to the power of representing functions as infinite series, a technique he would later exploit to solve a wide range of problems. The delay in the formal publication of method of fluxions until 1704 had significant implications. By that time, Leibniz's calculus was already well established and widely used. The delayed publication contributed to the priority dispute between Newton and Leibniz, and it slowed the adoption of Newton's methods outside of Britain. Had Newton published his work earlier, the history of calculus might have unfolded quite differently. Newton's approach focused on problems of instantaneous rates of change and accumulating quantities. He sought to understand how quantities change over infinitesimally small intervals of time, and how these changes accumulate to produce overall effects. These ideas were crucial for understanding motion, gravity, and other physical phenomena. For example, the problem of determining the velocity of a projectile at a given instant requires understanding the instantaneous rate of change of its position with respect to time. In summary, Newton's method of fluxions represented a groundbreaking approach to calculus, providing innovative solutions to problems concerning tangents, areas, and rates of change. Although its initial circulation was limited and its publication delayed, method laid the foundation for the development of mathematical analysis. His specific intellectual goal included finding tangents to algebraic curves. Newton's method of fluxions, though formally published in 1704, circulated in manuscript form for decades. This delay significantly altered the trajectory of calculus development, particularly considering Gottfried Wilhelm Leibniz' contemporaneous and published work on differential calculus. Newton's approach, developed primarily between 1665 and 1671, centered on the concept of fluxions, representing instantaneous rates of change, and fluents, representing quantities that change with time. The work detailed novel methods for finding tangents to curves, determining areas under curves, and solving maximum-minimum problems. Newton's method offered a systematic approach to these core calculus challenges. To illustrate, consider the problem of finding the tangent to the curve described by the equation y equals x to the n. Newton's fluxional approach involved considering y and x as flowing quantities, with fluxions designated as y dot and x dot, representing their respective rates of change. Differentiating the equation yielded y dot equals n times x to the n minus 1 times x dot. The slope of the tangent at any point thus became y dot divided by x dot, which simplifies to n times x to the n minus 1. This technique, while lacking the rigorous limit concept of later formulations, provided a computationally effective method. Newton employed a dot notation to represent fluxions such as x dot and y dot, signifying the first derivatives of x and y with respect to time. Double dots, such as x double dot and y double dot, denoted second derivatives. This notation, while visually concise, proved ultimately less adaptable and intuitive than Leibniz notation with dy dx, particularly in complex multivariable calculations. Leibniz notation, due to its explicit representation of differentials, facilitated clearer manipulation of derivatives and integrals. Despite the elegance of Newton's dot notation, the scientific community widely adopted Leibniz notation for its versatility and clarity. Method of fluxions proposed a fundamental relationship between fluxions and fluent differentiation and integration stand as inverse processes. Determining the fluxion amounts to finding the derivative of a given fluent. Conversely, finding the fluent requires determining the integral of a given fluxion. This insight formed the basis for solving various problems through calculus. For example, given a fluxion representing the velocity of an object, one could integrate the fluxion to find the fluent, representing the object's position as a function of time. In the context of differential equations, Newton's fluxional method provided a means to solve equations involving unknown functions and their derivatives. Given a differential equation, such as dy dx equals some function of x, Newton's approach involved finding the fluent y of the fluxion, dy dx, by integration. While Newton's method provided practical solutions, it lacked the mathematical rigor and systematic theory of differential equations established later through the works of Cauchy, Picard, and others who formalized existence and uniqueness theorems. The delayed publication of method of fluxions proved consequential. Leibniz published his findings on differential calculus in 1684, gaining wider recognition and influencing the development of calculus across Europe. Newton's reluctance to publish his work promptly created a complex situation, as historians would later understand the scientific record. Acceptance of Newton's methods, and indeed his priority, became more pronounced in Britain. Mathematicians like Colin Maclaurin and Brooke Taylor built directly upon Newton's foundations. Maclaurin's work on infinite series and Taylor's formulation of Taylor's theorem are deeply rooted in the concepts presented in method of fluxions. These later mathematicians provided more formal and rigorous treatments of these ideas, addressing some of the initial concerns about the lack of explicit limit definitions. The work laid crucial groundwork for the development of differential equations and mathematical analysis, while Newton's presentation lacked the rigorous formalization of later mathematicians such as Cauchy. His intuitive understanding and innovative techniques provided an essential starting point. Cauchy's contributions to the definition of limits, for instance, provided a formal foundation for the concepts that Newton had approached intuitively. Reflecting on the legacy of method of fluxions, one recognizes its enduring significance as a foundational work in calculus. Even with its limitations in terms of modern rigor, its impact on shaping the development of mathematical analysis remains profound. The concepts and methods introduced by Newton in this work continue to resonate throughout physics and engineering, where calculus stands as an indispensable tool. Newton's calculus, despite its initial lack of fully rigorous proof, proved to be stunningly effective in describing the physical world.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.